All right, hey all, so I think we're going to kind of get started here. So there is going to be a lot of code and general links and whatnot in the slides. So rather than having to try to take pictures and follow along that way, I did put all of the slides already up at this link. So if you want to grab a picture of anything, this is kind of the slide to do that with. And then you can follow along either through the presentation or just come back to it later and kind of go from there. Cool. And then I'll also have it at the end of those slides too, so if you don't manage to get it now, that's cool as well. All right, so hey all, my name is Ruiz, and I am a developer relations engineer with Google's ML team. So while my team covers a variety of different topics, my main focus is on mobile and IoT, and essentially how you would run machine learning inference directly on those devices. So today my overall goal is really just to introduce you to the new Google AI Edge umbrella that we had ended up announcing at Google I/O this last year, which includes a collection of tools specifically around on-device machine learning, including how you would bring some of your own ML models from different platforms or train your own, and then also do that inference step. And mainly the focus here is so that you don't have to really be deep into the data science side of things to be able to use this machine learning on your devices. Just because as Android developers, we kind of know there's already so much other things that you're worried about. You don't need to go dig into that side as well. So before we get into all of that though, I just want to go ahead and cover a few really high-level machine learning concepts. So while a traditional program takes a known input and a known function, or essentially a set of rules, to produce an output, machine learning actually takes a set of known inputs and known outputs, then it tries to figure out what the function is between the two so that outputs can be generated based on new inputs. This process is called training. It's one of the main technical things that a lot of developers think of when they're thinking of machine learning. Though honestly, it's not really the main focus of this presentation since, again, a lot of times we as developers for Android tend to just be given our models that have been trained and optimized by somebody else. That said, I am going to show you a little bit today about where you can go to train your own models or convert other models from different frameworks, just so that you can have those, just because it's not exactly uncommon that you kind of end up doing everything when you're working in mobile development. So understanding where you can go to learn more and kind of figure out the rest of it is always nice. The next thing to know is that machine learning models do not provide exact answers. Nor do they really always give you the correct answer, so it's just something to be aware of. What they do is they are making predictions based on what they've learned during that training phase. All right, so the main part of Google AI Edge that I focus on is the on-device machine learning inference stage, or the part of machine learning where you're taking some input, running that through a model, and then getting some kind of output. So while you can run machine learning inference directly in the cloud, and a lot of people do, it's a perfectly valid and useful way of doing things, there are a few solid reasons for why you may want to do everything directly on the user's device. So the first one is that this functionality for your app will be available even if the user is offline. So if they're on the metro or in a rural area, they still will be able to use the features that you have built for them in your app. Privacy is also preserved just because the user's data is never actually leaving their device. And then finally, you're able to keep costs a bit lower just because that inference is being offloaded to the user rather than having to go up to a server somewhere for actually doing that processing and paying for the cloud backend and all that stuff. So right now, while it does seem like just everything is about AI and machine learning, because it kind of is and it's a thing, on-device machine learning, though, has actually been a thing for a while, especially with Android and TensorFlow Lite launching back in 2017. That said, it has always been kind of complex. We have released some tools like MLKit that makes common operations just a whole lot easier, but doing anything outside of those predefined jobs got right back to the problem of needing to know how to design, build, and optimize your ML features, which again, isn't necessarily going to be in the skill set that just a lot of mobile developers have. So to address those two extremes, a bit over a year ago, we released MediaPipe Task on Android, iOS, web, and Python, which does work on the Raspberry Pi as well, which is kind of cool. I've tested on the 4B and later. But it handles a lot of the pipeline from data in to results out. So we still support a lot of common tasks, but we've made it so that you can bring your own models to change various settings and do other things that you actually need in your apps to take advantage of things like flow control and pre and post processing for you behind the scenes of this framework. And then what's nice about this is that the TensorFlow Lite runtime is still driving that inference. So you can actually have your own custom models for a lot of the tasks, just like you would with the traditional interpreter API. So image detection, object detection, that kind of thing. You can just kind of pop over your models without having to do a whole lot of extra work to customize those models just because we have another tool. So currently we support about 20 different tasks out of the box. So not all of them are going to be listed on this slide, just for sake of keeping things easy. But you can find the samples for everything on GitHub, which I'm going to link to at the end of this presentation. And then if you have any questions on those two, definitely let me know. I've worked on all of the Android samples, so I can kind of walk you through what they do, the other questions you have and whatnot. I would love to collect that feedback from anybody too if you're interested in using any of these. But for the next part of this presentation, I really just want to introduce you to some of the things that are available with MediaPipe, as well as a bit of information about how you would do these things with the older TensorFlow Lite interpreter API, so you can see what has been abstracted away and understand what's happening underneath it, so if you do need to know those details. So I'm going to go ahead and get started with going over image classification. So since it's really kind of our hello world in machine learning, essentially this looks at an image and then it assigns one or more labels to that image, trying to classify what's in it. So for example, with a single image classification model, this image of a cat will likely appear as cat, since it is the most pronounced item in that image. And then for how that classification actually happens, the underlying model that I'm going to cover is using something called a convolutional neural network. So this tool's main way to approach image classification is just to look for patterns within that image, and then basically try to find those same patterns in new images when it starts looking out for them. So getting back to the cat image, if we say that we have thousands of cat pictures and then we're training a model with those, we can start noticing trends in things like the ear shape, the eye shape, and the nose shape. Now, if we look at the brand new pattern or image and try to find those patterns, we should be able to identify those items, or at least most of them, depending on the image, so that the model can say, yes, there is a cat here with some level of confidence. And then the next thing to know is that this classification happens across multiple layers of an image. So for example, Android may use an ARGB image as coming in from the camera. Since the alpha layer doesn't really give us much information, we can just go ahead and drop that. But then the rest of the colors are looked at as individual pieces of these, basically the data structures, so that it can be classified against those. Mainly because in different colors and layers, you're going to see different patterns based off of the structures that are there. Oh, I started playing music. Anyway, so basically what's happening though is these are being turned into 3 separate arrays based off of the height and width, and each of these matrices are based off of the color. Okay. Anyway, so while that isn't super important when we're talking about MediaPipe task, since a lot of that is abstracted away, it does become really useful to know once you start directly working with TensorFlow Lite, or if you kind of go off to make your own models to work with TensorFlow Lite or MediaPipe, depending on what you're doing there. So in the next few slides, I'm going to show you how you would do image classification with the TensorFlow Lite Interpreter API, which earlier I mentioned is unnecessarily complex. So I'm going to just kind of show you that so you can understand what's happening, and then you can hopefully appreciate MediaPipe as much as I do. And then I'm going to go into MediaPipe task. So aside from importing the dependency, the first thing you'll need to do is create the interpreter object that does the actual inference. So you're going to need to load in the model file that will have to be stored locally on the device, because this is all on-device machine learning. So that, because nothing is going out to the cloud or anywhere else, it has to reference that model based off of it being saved in like your assets folder or somewhere else on the device. You can then set some options like how many threads the interpreter should utilize, or whether or not it should try to run on specially hardware for doing that inference, so like your CPU, your GPU, NPU, what have you. One thing worth catching here too is that the interpreter API doesn't automatically support labeling through metadata on models, so you do need to go through and abstract those labels beforehand so they can be paired with your results later. And you'll likely also want to do some pre-processing on your images before it's actually run through the interpreter. So here this is going to include things like resizing your images so they match up to what your model was trained with and expects. So if your model was trained to expect 28 by 28 pixel images, then you're going to resize to match to that just to get your better results. You're also going to want to check the camera rotation and take that into account. So if the image is rotated 90 degrees, those patterns aren't going to be as noticeable as if you oriented everything to kind of fit with what the model was trained with. And then after all of that, you can just take the image and convert it into a tensor image based on the pre-processing steps. And then this is actually where it starts to get tricky. So you're essentially going to need to create float buffers that match the output shapes of your data. So with image classification, it's not too bad. Generally, you're just going to need a single array that is the same length as however many labels are in your data set. All right, cool, man. Anyway, so from there, you can call run on the interpreter with the buffer from your tensor image, as well as that new output buffer. And then you can go through whatever steps are necessary to turn the output buffer array into readable or usable information within your app. All right, so that was a lot, but it is kind of the unfortunate reality and complexity that you need to know if you're doing kind of that custom on-device ML solution setup. But for things like image classification or the other common tasks that I had mentioned earlier with MediaPipe, we do have that MediaPipe task. So now I'm just going to go over how you would do exactly the same exact thing. Right here, I'm just image classifying on a cat again, but I'm going to go over the newer tooling. So again, you're going to start by bringing in that dependency, but I'm going to skip that part. We've all seen a build file, so whatever. The next thing to do, though, is to create the actual object that will do that classification for you. So this pattern is pretty standard across all of the features in MediaPipe task. We've made it pretty uniform. So if you are more interested in something like gesture recognition or object detection, you would use the same exact patterns as you're moving through this. So I'm just going to kind of cover it so you have those foundations. So there's two levels of options that will be combined to create the classifier. The first one is the base options, which we can create using a builder pattern. So this is essentially going to wrap common functionality that you'll find across the various tasks within MediaPipe. One of the properties that you can associate with that base options object, though, is the delegate. So this is kind of what we saw earlier with TensorFlow Lite, where it was, hey, am I using the NN API or the GPU or what have you? So we support that with just this one line, essentially, in MediaPipe. So right now we support the CPU, which is slower, but it's on every device, every model supports it, and the GPU, which you can use for kind of delegating some of these underlying methods and whatnot to it to be a little bit faster, but you're not guaranteed that a model supports that. And then for these next two lines, we're just setting the path to our TF Lite model, which again is going to be the same one that I used in the TensorFlow Lite example. And then it has to be stored on the device again, so it's all being saved in the assets folder within your APK or wherever. And then I'm creating the base options object here. So while this task is actually using a regular TF Lite file, we do have some .task files, which are essentially just bundles of TF Lite files that run in sequence, but I'll kind of go over that a little bit later as well. And then just like the previous example, because this is all on device, oh yeah, so the model is going to be there. They're generally pretty small, so you can just bundle them in. If you do have models that are a little bit larger, or you just don't want to bundle them in with your APK because of sizing or whatever, you can just pull them off of like Firebase storage on first run, save them on the device, and then move from there. So you have a couple different options as long as you're able to bring that in. And then this next block is where you're going to create the image classifier specific options that we use to create the actual image classifier that does the work for you. So here you're going to be able to set the minimum score threshold, or essentially how confident the model needs to be in what it's seeing before it returns those results to you. So we saw a little bit of this in the TensorFlow Lite example where it was just like, oh, sort these and then give me the top three. So here you can just say, set the max number and it'll just give you those max number results back. And then we have something here where you can set the running mode, which is going to vary depending on if it's a live stream, a still camera, or a video file. So the first two items basically just get rid of that need of that other stuff, and then these ones are going to be telling it like, hey, how should I handle flow control? So if you're doing something with like a live stream, because the frames are coming in from the camera potentially faster than the interpreter can deal with them, it'll handle the actual buffering, dropping the older frames, and keeping you kind of on track as it's doing that inference step. And then for the last step here, just to create the initial options, you just want to associate the base options from the first block on this slide with the new image classifier options builder that you're creating. And then these are just the listeners that are actually associated with it if you're using the live stream. So because it is handling that flow control and everything is happening asynchronously, then you have these callbacks so we can say, hey, here are my results, send them off to wherever you're doing whatever in your app. If you're using a video or a still image, everything is just able to happen synchronously, so you don't need to worry about having callbacks and trying to make sure you're moving results back and forth throughout your app. And finally, you can create the new options and use them to create the new image classifier object that will handle pretty much all of that major work. On this last one here, cool. So from there, you're just going to want to create a new media pipe image, so kind of like you did with the tensor image, that's going to be classified using the classify async method when you're using a camera stream. That's just because, again, those are actually asynchronous, so it's taking a bitmap from the camera, converting it, and then passing that around. If you are using still image or a video file and everything is happening synchronously, then you can just use a classify method. And then that is pretty much it for the media pipe side of things. As I mentioned, at least on the code side, all of the different tasks follow very similar patterns, pretty much the same patterns. So once you know how the image classification one works, you can use the same thing for object detection or some of the other things. So what I want to do now is kind of just cover some of those more commonly used tasks, just so you know what's there and what you can start adding into your apps. So this one here is object detection. I'm actually showing the results object that you would get on any of our platforms. So this object is going to be the same information and whatnot that you have on Python, Android, iOS, what have you. But this is going to include both labeling the object as well as giving you a bounding box with an X and Y origin point as well as the height and width to actually kind of localize where that object is. And then we also have a set of tasks dedicated to finding landmarks on people, including general poses, hands, and faces. So the pose landmarker task can find 33 points across a person. The hand can find 21 from the base of the palm, each of the fingertips, and all of the joints on the hand. And the face landmarker API can detect 468 key points that can actually be grouped together. We have some other things for creating these collections, for isolating the lips, the eyes, the brows, and the edging of the facing. The other cool thing about this too is that it doesn't just stop with finding landmarks, but we also support going a step beyond that to do things like classifying different gestures, which you can see in the center image here, where it's able to see hey, I'm doing thumbs up, thumbs down, a closed fist, open palm. So what is kind of interesting about this is that something like gesture recognition isn't just running one model, and I kind of mentioned this a little earlier, but in running multiple models in a pipeline to kind of pull off this more complex task. So basically the first one is going to attempt to detect that a hand is even located within the image or frame or what have you. If it doesn't find one, it actually exits the process and just kind of moves on to iterating or doing whatever it's going to do. So you're not constantly oh, I didn't find anything, so now I'm going to check other stuff. It'll just kind of early exit. The next phase then is going to attempt to detect those landmarks on the hand, which is what we saw in the previous slide. And then the third one is something called vector embedding, where it's just checking for similarities. It's some machine learning concept stuff there. And then the final one here is that's going to do the actual recognition for those different gestures. So along with gestures, the face landmarker task does use a similar pipeline to find and predict with kind of some level of confidence, 52 different features of expressions. So you can try to recognize if a person is doing something like opening their mouth or raising their eyebrows. So if you're working on a camera app and you want to make sure you're taking a picture exactly when everyone has their eyes open and they're smiling, you can kind of use this as a tool to augment that and help you out with your feature. Plus there is one more model running in the face landmarker pipeline that attempts to predict approximate 3D surfaces, which lets you pull out these facial transformation matrices that can be used for augmented reality when you're adding those kinds of features to your app. So this raccoon face that I put over mine. I think there's a talk tomorrow on OpenGL and augmented reality too, so if this is something that interests you, you can probably take the same ideas and apply it with that. I haven't seen it yet, but I'm actually going to go check that one out. And then the last of the common vision tasks that I want to bring up is called image segmentation. So basically what this does is it provides a category prediction value for all of the pixels in an image or a frame based on what it thinks might be there. So like a person or not in the image on the screen, or you can see like it highlights my glasses or neck or some other things what the model was trained with. So what's interesting about this though is it's actually looking at each pixel in relation to the pixels around it and using those to apply weights to kind of figure out, hey, what is the category for this pixel, rather than just like, oh, it's gray, cool. All right, so now that you know a little bit about on-device inference with TensorFlow Lite and MediaPipe Task, I did want to get into a little bit of basically how you can work with machine learning models as an Android developer. So on our official documentation pages for MediaPipe Task, we do provide a set of default models and task bundles for every one of the tasks. So if you just want to like try it out, the model is already online, you can just grab that, plug it into your app, call it good. If you only want to use the default models, it's great. But let's say that the default models don't really work for your app. So in that case, we actually provide a tool called MediaPipe Model Maker that will help you train new models using existing architectures based on the data that you provide to work directly with MediaPipe Task. So for now, let's actually go over how you would do this with like object detection. So to get started with training your own model, first you need to collect your data. I mean, that's kind of the big important step of all machine learning training. So generally though, this is just going to be a whole lot of pictures of objects that you want your model to detect. And then you can break them into two groups for training and validation. So for my purposes, I'm actually using a program called Label Studio, which runs locally on my device. It worked on Mac. I think it works on like Windows and Linux as well, but I would have to go confirm. But anyway, so I created two separate projects, one for training, one for validation, and that's where I put my data. After your data is partitioned, it's time to label each object that you want your ML task to be able to distinguish. So I'm using Label Studio here again, but this is honestly a really long and kind of just tedious process where you go into every image and you highlight each object to apply the proper label to it. There are some things to be aware of here though, like how to handle partially visible items for overlap or overlap, I guess. But that's kind of a bigger topic. Finally, it's time to actually export your data into a usable format. So in this case, I just put everything out there as a JSON file, and then also the collection of images that are related to it. So like it knows, hey, here are the list of objects, their height, their width, their location, and here's the image file name that I'm like referencing off of this. And then you can start your training. So the MediaPipe Model Maker tool is available on Colab. So it's a free to use tool. It's all on the cloud. So you can just kind of go in, load up this like sample that we've already put together. You can give it your data and then output a new object detection model based off of that. So essentially, what you're going to do is you're just going to tell Model Maker, hey, this is the architecture I want to use. You give it a set of kind of configurable parameters, and you call create to start training, and then it'll kind of go through and like segment out your data for training and validation, and like start working on outputting that model. After that's all completed though, you should be able to download that model and then plug it into your app to use it just like one of the default models. So I actually have a video on YouTube if you want to see this whole process from beginning to end. It is a little bit longer, so just kind of be aware just because there is some tedious steps to it. But that's for like annotating data, how you actually use the software, how you actually run through the collab, that kind of fun stuff. So here I'm actually using one where I trained it for these little wooden toys. And in this example, I'm running it on the Raspberry Pi. And what's kind of cool about that is it's using the same pipeline and the same exact model that I've used on Android, just on the different platforms. So if you are supporting iOS as well, or web, or what have you, you can take the same model and that whole process and just plug it into whatever platform you also need to support. We also support retraining for more complex tasks, so like gesture recognition. So the default model right now supports 7 different gestures, which you can see here, but maybe you don't care about like the victory sign or pointing up, or the default ones that we have here. So in that case, you can actually use MediaPipe Model Maker with your own data set of static gestures, like I'm doing here for the game rock, paper, scissors, where it can detect these 3 different gestures and then come back with none when it's shown something like a thumbs up. So similar to object detection, I have examples for this already up on GitHub, up on YouTube, all of that's through the official MediaPipe samples GitHub, which I'll link to at the end. And then this question always comes up too, so like how would you do this with like dynamic sign language? We have an example for that as well using the Landmarkers API, and it's actually recording video fragments and then running that through its own custom TF Lite interpreter API calls as well, so you can actually stack these things to do even more like elaborate processes. So while that is useful and all, this year at I/O, we actually released support for converting PyTorch models to work with Google's AI Edge tools, so including TensorFlow Lite, MediaPipe Task, which has actually been one of the more commonly asked for things from the dev community. So like I haven't actually been to a droidcon or a meetup in the last couple of years where this hasn't been a question that has come up at some point, like how do I use my PyTorch models with my Android app using these tools? So to give you an example of how this works, the Python code on the screen here actually came from the, it actually takes the ResNet model that was trained with the PyTorch framework, converts it to the TensorFlow Lite format, and then it exports that with just a few lines of code here. One thing worth mentioning here though is that you do need to know a little bit about the model to be able to do some of this stuff. So like here you have to know like, oh hey, the shape of this one is that 4x3 by 224 by 224, meaning it's taking those three colored layers that you have, like we saw with the cat one where it was red, green, blue, and they're all 224 by 224, and that's what it's expecting for the size. You don't have to get super deep into all of that. It's just kind of something to be aware of. We also have another tool called Model Explorer, where you can just plug in that model and you can see those details at like the top of the screen. If you do want to take this a step further though, we also support dynamic range quantization during this conversion step, which is kind of cool. So basically what it does is it will help you get your model to roughly a quarter of the original size after that conversion, so that it'll be even better for running on devices because you're able to reduce that size and keep pretty much the same quality of the outputs from it. So that's pretty much it for standard image classification, because again, that is kind of our hello world example for machine learning. But this does work with the, we do have a few different PyTorch examples. So we have the image classification one, and we have one for image segmentation, which is what you can see on the screen here. And then one thing that's kind of worth noting too is that last column is after the quantization step. So that last column is a quarter of the model size, while still giving you like pretty much the same quality that you get from the original mask that we were getting off the PyTorch model. All right, and then so for the last thing, I just kind of wanted to get into generative AI on device, since it is kind of the like big hot topic right now. So there's two different types of generative AI that we support running completely on device right now. There's image generation and text generation. Both of these are considered experimental, so something to be aware of, and they're more meant for prototyping and just testing out proof of concepts rather than putting in your apps right now that you're shipping into production. That said, the teams are working right now on reducing model size, increasing speed, all this other stuff. We're just very much in the early days of, hey, can we do this? And then we'll do it better. So I'm going to start with image generation. So in this case, we're using something called diffusion to generate new images based on a text prompt. So essentially this works by taking some text, figuring out what the keywords are related to what the model was trained with using something called a text embedder, and then creating a large amount of just kind of initial noise, which is kind of that staticky part that you see right there, that then ends up going through and being denoised as the image goes through these different iterations. So what is cool about this though is that you are able to create a new image completely in an Android app within, I say a few seconds. It's probably like 10 seconds on like an S24. But again, we are working on improving that. And this is a little bit slower because I am showing the keyframes as they're going through rather than just like, give me the final product. So there's some extra processing happening there. So to actually implement this into your prototypes though, there are a few steps you have to run through. So the first one is that you need the model to, with a compatible architecture. So we have a handful that we recommend in our documentation, and we also have some tools for converting other models to work within the like TensorFlow Lite framework setup. Once you have those models though, you can just load them onto your device, either using ADB Push or the File Explorer that's built in Android Studio. And again, I've had some luck with using like Firestore and just pulling things down at the first load rather than trying to do all of this. So like if you're sending this off to somebody who doesn't have Android Studio installed on their machine, they can just hit the button and download the model that way. Once the model files are in place though, you can follow pretty much a similar pattern to what you saw with the other MediaPipe task. But this time you're going to create the image generator object. And then you're going to set the path using the set image generator model directory, because it's going to point to an actual directory of multiple files. So you just give it an absolute path rather than using the assets folder that you would have before. Then after your image generator is created, you can then start generating a new image with just using a one-time generate call. Though this is going to only return like the one finished image rather than the extra key steps that are going along with it. The 3 key parameters that you're going to need to pass in, though, are the text prompt, which describes the image, the number of iterations that you want the model to go through for when it's creating the image, and the seed value, which is going to be what you can use to replicate the same image over and over again if you're using it as like an asset in a game, or if you want to be able to say like, hey, can you generate the same thing over again? For what it's worth, I tend to just use 20 for my number of iterations because I think it's kind of a good balance between speed and quality, and the seed value can be whatever, so you can just default that to 0. If you do want to display each iteration, it gets a little bit more tricky, but still not too bad. You can set those input values, though, before you actually call the generate call. And then you can just repeatedly call the execute function just over and over again for the number of iterations that you want to go through to kind of move through each iteration step manually. If you do pass in a true value for it to say like, hey, I want to see this iteration and keyframe, then you can just pass in true, it'll return that, and you can just kind of keep cycling based off of that to display things in your app. And then where I actually think this gets even more interesting is that you can take advantage of the whole pipeline aspect of MediaPipe to provide guidance to generations through something that we call plugins. So right now we support 3 different types. So there's the face landmarker, depth, and edge detection. So this is going to essentially let you provide a base image and then use that as the foundation for the noise generator so that you can create new images that kind of reflect that base. So here you can see we have like a picture of a car and it makes another car in kind of that same shape. Or I have a picture of myself and it's like, oh yeah, you're kind of looking that direction. It'll base it off of that. That said, this does add a little bit more complexity to the process, just because you are adding some extra steps to the pipeline, but again, it's still relatively minor. So using the face landmarker plugin is my example here. You need to provide both a task model bundle for the face landmarking, just as it does need to use that to find landmarks and uses that as the base. And this is the same one that you would use with the regular face landmarker task that we saw earlier. Plus there's a new plugin model that we also provide in our documentation. You'll also create 2 new options, or rather a new options object that sets basically how confident the model should be in the face before using it as a foundation. That way if you upload an image, it doesn't detect a face, it doesn't bother going through this whole step and causing issues later on down the line. From there, you can create the image generator just like you did before, but now it'll pass in the additional conditions options object over to it. And after all of that, you can just pass in the new base conditions image, so the one that you're going to use as the foundation, and the condition type to let it know, hey, I'm doing this with a face or edge detection or what have you. So in this case, I'm just using face. But you can pass that into set inputs or the generate call when you're creating that new image, just like you did before. It's just another parameter that can be added. And then for the final part of image generation, we support something called low rank adaptation, or LoRa, which allows you to apply additional weights and training to existing models, which is going to let you essentially customize generation for your app. So this technique, along with a training file that we've already put together and included in our samples, will let you provide those additional images to guide that image generation so you can have specific objects or people or image styles. One of the main things that we think people use this for, though, would be for like marketing and things and whatnot in your app. So if you have a product and you're like, yes, I want to make sure I'm including this teacup we sell or whatever in all these images that we generate, then we can just kind of make sure that that's included and it'll be the ones that you have trained it with. So to show this in practice, though, in this example, I actually trained my own LoRa weights using a whole bunch of Android figurines that I'm sure a lot of us have too many of. And I'm associating it with the unique identifier monadicos Android. So essentially that's just a fancy term. It just means like unit. It's the way of making sure that it's unique within the whole data set. But basically how this works is I uploaded just a handful of images up to a cloud storage bucket. And then I'm using a collab that we've put together, it's already online, to pull those down and retrain these weights. And then once I had those, I just moved the files onto the device in the same way that I did with the initial image generation model. And then as far as working with the code, the only difference is that I really needed to include this set LoRa weights file path value. And then everything else just kind of works exactly like it would with normal image generation without the weights. All right, and then the final thing that I want to talk about today is also kind of the big new shiny thing that everyone wants to talk about. But we recently released the MediaPipe LLM Inference API for running LLMs, including the newer Gemma model, directly on the device. So you can use this for things like smart replies, email composition, text rewriting, summarization, text classification, and kind of a whole lot of other things. We're hoping as developers really refine their models and figure out what they want to do with these things so we can kind of optimize for that. The Gemma model that we recommend right now is the 2B model. It's the one that I'm using here in this example. So it's not quite as in-depth as like the 7B, but I do think we're making good progress right now on just getting more robust models working within the constraints of mobile devices. So as we keep putting out like 9B and 7B and all the other ones that we've just been doing, the ones that are still running on the smaller parameters are taking the things that we learned building these bigger ones and making those models even smaller. So maybe next year it'll be half the size, the year after that half the size again, as we continue through here. So to give you kind of a point of reference as well, this is actually not sped up. This is exactly the speed that I'm able to run on an S23. With just everything running that way. But I have been able to run these Gemma models on like a Pixel 6 and still have pretty good speed as well. Before I dig into the code for this though, I did want to just kind of go over what exactly is happening so that you have a better understanding of basically what the code is doing before you start messing with it. So when you have some text for a prompt, it does need to go through something called a tokenizer. I didn't really get into this with image generation, but it's kind of the same thing that's happening there. This is essentially taking some plain text and then turning it into a series of numbers so they can be processed by the embedder that's in that model, which is, again, pretty much just some code that's going to compare that text and figure out similarities and that kind of fun stuff. On top of the text that the user enters, each model has its own specific format for denoting the start and the end of the prompt, along with some other metadata items that also count as tokens. So that's something else to be aware of. It will send a special token for basically like end of prompt, so you know when it stops generating and you can kind of react to that. So for the Gemma model, there are 256,000 tokens, or essentially numbers that are used for building out these words, in the vocabulary that the tokenizer can convert plain text to. So this is also the same tokenizer that's being used by the Gemma 7B and the Gemini models. I don't know if it's the same one being used by like Howley Gemma and some other stuff. I'll have to look into that. But here I'm just using the output instead of the input so I can make this graphic. But what's happening is the token mapping is going to be the same. So you can see I added some white space around it and highlighted these different tokens that are there. But a lot of it is going to be common English words, punctuations, like accent characters, and then some smaller pieces that aren't as common in English, but they do make up other sounds and words, so you can kind of piece those together. Once you have everything tokenized, it's actually time to send all of that information over to the model. So what ends up happening here is that the model looks at all the tokens that were input, then it comes up with a confidence score for every single token that's in that dictionary, for it being like the next word that's going to be output as the generated token. So the sampler, which is another component within this whole pipeline, takes those predictions and it decides, hey, which one of these tokens should I actually like output as the official output? So there are a few different ways that you can actually approach this. So the sampler could either use a greedy approach where it just says, hey, this is the most confident one, so I'm going to use that. The problem with that is it tends to always, well, it is always going to be the same, but it also tends to not really have a natural feel to it. So there are some other things like top K results and temperature, which I'm going to kind of discuss later, that can add some entropy into this whole pipeline to make it a little bit more kind of human-y feeling. Once the output token is selected though, it's actually sent back to the model, which is then going to use all of the original inputs, every generated token, and that new token, and use those as kind of weights and whatnot to determine what the next token should be after that. So it's continuously just kind of feeding in on itself to figure out what it should create next. And then so before wrapping up, I am going to just kind of dig in a little bit of how you would use this. So this is all coming from the sample code. So if you want to go and grab this from GitHub and go over that, you can kind of see what's going on. But the first thing you need to do is make sure that you have a model loaded on your device, because again, on-device machine learning, it's all completely happening locally. So we do have a default model that you can get from Kaggle for Gemma, Pi2, and a couple other architectures. And then we also have the newer PyTorch generative API. So if you have your own LLM model that you want to convert, you can also grab that and kind of go through that process of doing that conversion. As for the actual LLM inference API, though, you'll create an options object, just like you did with everything else in MediaPipe, set the path to the stored model, and then from there, earlier I mentioned that you also have some values for configuring the sampler, so you can actually set those here. So the top K is going to represent how many of the top predicted values should be available to be selected from when you're actually picking the next token sequence. And the temperature is more about the entropy that's being applied with those prediction values. You'll also want to add in your result listener here, so if you're using the async option, which in this case I'm just using a separate flow structure. And then finally you can just pass in your prompt to the LLM inference object that was created on the last slide to start generating your responses. So there's actually a generate response, which is synchronous, and a generate response async, which is going to be your async version of this. And then before wrapping up, I did just want to bring up that since this is all considered experimental still, if you do want to add LLMs into your app, Firebase has some tooling around cloud-based Gemini and Vertex AI, which is worth checking out. I did confirm before coming here that this does work in Europe, so you're not going to run into issues of like, I can't use that there, so it doesn't matter. And then the Android team is working on their own stuff as well with having a shared general model that you can apply weights to without any fine-tuning. So that's all up on their EAP and that fun stuff in their documentation. If you want to learn more, there are links here. So this is the official AI Edge documentation page, as well as the link to the GitHub samples. It looks like a couple people want to take pictures, so I'll give you that for a second. All right, and then absolute last thing, feedback. So I'm going to be at the event all week. So if you want to let me know, like, what are you working on in the ML space? What do you want to be able to use this for? Have you tried any of this? Are you having trouble with it? Any feedback that I can get, I take it back to our engineering team. We use that to improve our products, make things that are just better for the developer community in total. So yeah, compliments, complaints, everything. I will appreciate all of it. And then here again is the link for the whole slide deck if you want to grab that. Cool, so thank you.